I welcome you all in this lecture on linearity and non-linearity in systems, and this is part of our course, that is modeling and simulation of dynamic system. See, when we talk about modeling of a system, it is very important to understand whether your system is linear or it is non-linear. Truly speaking, in nature most of the things are non-linear, okay. But the problem with the non-linear systems are that if you want to analyze it, okay, it is difficult and there is no generalized method to deal with the non-linear system. So, there the actual problem comes. So, here in this lecture we will be looking at how can we linearize these non-linear systems, okay, and we will take up some of the examples. So, previous few lectures we have been seeing the individual building blocks which comprises of systems in say mechanical, electrical, pneumatic, hydraulic and thermal. Now, the real physical system will be combination of any one of these, okay. So, we will be coming across combination of different discipline building blocks, and these different discipline building blocks can be used to model a complicated system. Say if I take an example of say electric motor, then here you see that it involves both electrical and mechanical elements. The electrical elements are say armature, inductance of the armature, resistance of the armature, and the mechanical element could be the load which it is going to drive, okay. So, that is going to be there. Now, when we combine these two different systems, say mechanical and electrical, it is assumed that the relationship for each block is linear, okay, and with this assumption only we will be able to combine these different blocks. Now, if some relationship are non-linear, a linear approximation can be made for such type of cases. Now, let us see the characteristic of various type of non-linearities. The first one, you can see that with increase in input the output also increases, but after a certain value of input their output remains almost constant, and this type of behavior is what we call it as the saturation non-linearity. Other type of non-linearity could be the dead zone non-linearity. If we look at this graph, now here you will see that for a certain value of input there is no response for the output, or we do not have any output response, okay. And of course, after some time output changes with increase in input. So, this type of non-linearity what we call it as dead zone non-linearity, that is there is no response or there is no output for the given input. And the other type of non-linearity could be the square law non-linearity, okay. That is here if you see the input and output, then you can see that the output varies almost with the square way of the input, okay. So, if I look at some of the reasons or causes or examples for these type of non-linearities, the saturation, as I said, saturation non-linearity, output of a component may saturate for large input signal, okay. So, if the input signal is large, then the output may saturate, okay. It may not vary at all for the given input. So, this type of nonlinearity, as I said, we call it as the saturation nonlinearity. Then the dead zone nonlinearity, as I said, dead space may affect signals, that is a small range of input variations to which your component becomes insensitive and you do not have any output from it. And square nonlinearity, if I want to give an example, we all know that say the damping force say for a mechanical damper is given by say damping coefficient into velocity, F is equal to CV. Now, here you can see that F is proportional to V. So, this is basically the linear behavior, but if it may happen that the damping force may become proportional to square of velocity for say high velocity operation, then this equation will be becoming like say F proportional to V square, and this type of nonlinearity, what we call it as the square nonlinearity. Okay. So, yeah, and there are many other ways of nonlinearity appearing in the system. For example, if your system equations has got some say sine and cosine terms, trigonometrical terms, they also make your system nonlinear. Now, let us look at how do we decide whether a system is linear or non-linear. Okay. So, to tell that, let us take a simple example of the spring. We are all aware of, I have discussed a lot about a spring, it is a mechanical system element, okay, and we have seen this when we were discussing about the mechanical building blocks. Now, if I take an ideal spring, then for ideal spring we know that the force is given by K into X, where K is the stiffness and X is the extension in the spring, or what we can say that the force is proportional to the extension X, and this relationship is what we call it as linear. Now, there is a characteristic of a linear system, and that characteristic is that they fulfill the principle of superposition, and that principle of superposition is that is for a given input, if you have some output, okay, and then for given another input you have some another output, then you can have the combinations possible, alright, and this is what we call it as the principle of superposition. I will explain it in detail. Say whatever spring example I was taking, if a force F1 produces extension X1, okay, and say another force F2 produces extension X2, then if I am applying a force F1 plus F2, then it will produce an extension X1 plus X2, okay, and this principle is, as I said, is what we call it as the principle of superposition, okay, and this is, remember, a necessary condition for the system to be linear. Another condition which we can say that is the another property which is exhibited by the linear system is this one, that is if say a force F1 produces an extension X1, then some multiplication of F1, okay, say CF1 is going to produce an extension CX1, okay, and where C is a constant multiplier. So, the thing is that if you have F1 is equal to, say in this case of spring, say K x1, then if I multiply here, so Cf1 will be basically k times Cx1. This is what I mean by it. Okay. So, these two conditions are fulfilled by a linear system. So, let us see graphically this. Suppose we have a spring, linear spring, and if I plot the force versus x here, then you can see that F is equal to Kx, which is the characteristic for the spring, and F1 is equal to Kx1 and F2 is equal to Kx2. Then if I combine these F1 plus F2, I should get Kx1 plus x2. Likewise, if I put Cf1, I should get C times Kx1. So, if this behavior, this type of behavior is exhibited by any system, then we call the such system to be a linear system. Now, the thing is that as I told to you in my opening remark for this chapter, that in nature most of the things are non-linear. Then the problem is how to analyze those systems. Okay. So, the real spring is a non-linear spring. As you can see here, if I plot F versus x for a real spring, then you can see that there is a certain portion here up to which its behavior is linear, but after that the non-linearity commences. So, how do we analyze this? So, what actually is done, that we assume linearity for some range of operation, and of course we ensure that our spring operates in that particular range. So, if we do this, then our linear assumption is going to be valid. Now, here as I said in this figure, if we assume that a spring operates in the central zone, then linearity approximation is going to be valid in this case. Now, for some systems, linearity can be assumed for operation within a range of values of the variable about some operating point. In this case, we assumed linearity about, say, in the central region, but it is not always necessary that things should be linear in the central region only. Okay. So, it could be linear anywhere, fine. So, we can assume operation within a range of values of the variable about some operating point. Thus, if region of operation is restricted to a narrow range, a non-linear system can be treated approximately as a linear system. Okay. If I am assuming that my operation is going to be there in that small region where the system is linear, okay, and this need not be in the central band, as I said. Now, this approximation is valid for most of the control system. Okay. Why? Because the control system purpose is to keep the control variable very close to the desired value. So, the control system will always try to keep your variable within a small range of desired value. So, as I said, within a small range, if I am talking about, then naturally in that small range my system is going to be linear, and this is one of the very reason for assuming the linear behavior of a control system. However, if the system is required to follow a variable desired value, okay, in that case one can analyze the system by linearizing it at several points along the curve. Now, So, what should be the procedure for linearizing a nonlinear system? So, let us see how actually we do that, how actually we linearize a nonlinear system. So, this is what I was talking to you, that is for a nonlinear system to linearize, what we can do the following. That is, here suppose this is my output versus input curve for a system, okay, and as you can see the behavior of this curve, it is a nonlinear curve. So, to analyze this or to linearize this, what actually is done is that we select an operating point. Say here I am selecting the P as the operating point, and then work with a straight line which is slope of the graph at that operating point. Okay. So, I draw a tangent at this operating point P, and then I work with this tangent, okay, or work with this straight line, and which is the slope of the graph at this operating point. And you know, say if this element is, if this segment is of length delta y and if this segment is of delta x, then I can always write delta y is equal to m delta x, which of course comes from the definition of the slope, that is tan theta, delta y by delta x, that is tan theta, okay, and which we represent as m. So, here what actually we have done, that we have represented this curve by this straight line, and the expression for this straight line is delta y is equal to m delta x, and this is how I am able to linearize this curve at this particular operating point P, okay. And as I said, here delta y and delta x are small changes in the output and input signal at the operating point. Now, we can see this thing, this delta y is equal to m delta x mathematically also. So, if I look at say the curve again, okay, for a general element with say input xt and output yt, the input output relationship, as I said, is shown here, which is actually a non-linear relation. Here the relationship non-linear, but of course I am going to assume that it is continuous. Now, what we can do is that we can expand the equation y is equal to fx into a Taylor series about the normal operating point, say x0 y0. Now, if I do that, this is what I am going to get, the Taylor series expansion. So, y is equal to fx, and this is f, which is f x0, that is where x0 is your operating point, plus x minus x0 by factorial 1, and evaluation of del f by del x at x is equal to x0. Likewise, you have the higher order terms. Now, if I assume the variation x minus x0 of the input about the normal operating point to be small, then I can neglect these higher order terms, okay. So, I can neglect this higher order terms, okay, and if I do that, this is what I get, y is equal to y0 plus x minus x0 by factorial 1 and del f by del x at x is equal to x0, or here what I have, y is equal to y0 plus, if I represent this as m, or the slope which I talked to you in my previous slide. So, here it is m into x minus x0, where m, as I said, it is del df by dx at x is equal to x0 is the slope at the operating point, and then I can write this equation as y minus y0 is equal to m x minus x0, or I can further write this as delta y is equal to m delta x. So, this is the same equation which I showed you graphically, and here I just wanted to tell you that what happens mathematically. Okay. So, basically mathematically we get the same result if we assume the x minus x 0 variations to be small, and we can neglect the higher order terms of the Taylor series expansion. Now, let us take a few examples. So, here I am going to take two examples. The first is the flow through an orifice, and the second I will be taking about the thermistor. Now, here you can say we have a orifice, okay, and there is a flow Q taking place through this orifice, and say the cross section area here at the orifice A, and the pressure at upstream and downstream side are P1 and P2. Now, in this case the discharge equation through the orifice Q is given by CdA under root 2 P1 minus P2 by rho, where this CD is the coefficient of discharge, A is the cross section area as I said here, and here rho is the density of the liquid, okay, and of course P1 minus P2 is the pressure difference, as I said, that is the pressure difference between the upstream and downstream side. Now, the question is, you can see that this equation is a nonlinear equation. Why nonlinear? Because this equation involves the square root of this P1 minus P2 term, okay. This equation is not a linear equation because you cannot apply the principle of superposition here, alright. So, our job is to linearize this equation, okay. So, let us see how we can do that. So, as I said, this was our basic equation, and suppose I assume in this basic equation that the area orifice area of cross sectional area of orifice is constant as well as the density of the liquid is constant, then I can write the constant terms together as say C, and these equations become Q is equal to C under root P1 minus P2, and as I said this equation is nonlinear. Now, to linearize this equation again we have to consider a certain operating point. So, if I look at this plot is basically between input and output. So, say I have input P1 minus P2 and output Q here, and if I plot this, then this is my nonlinear plot, nonlinear variation of Q with P1 minus P2. Now, to analyze this I take an operating point P, or to linearize I take an operating point P, and what we do next, we draw a tangent, okay, or slope line passing through this operating point. Then the slope of the line can be given as you can see, I can write the slope as delta Q upon delta P1 minus P2, okay, but this was our basic equation. So, I can write dq by d P1 minus P2 as this one, that is I can differentiate this equation. So, dq will be C by 2 under root P1 minus P2 and d of P1 minus P2, and from here I can write this value, that is dq by d P1 minus P2 is equal to C by 2 P01 minus P02, okay. Why P01? Because I am talking about this operating point. So, the slope is basically a constant C which comes from here and this value, and these values are values at the operating point, that is in this case the value at this operating point. Now, for small changes about the operating point we can replace the nonlinear graph with a straight line of slope m. This is what we have done here. Then the slope of the straight line can be given by delta q by delta P1 minus P2, and thus the linearized equation can be written as here del q is equal to m del P1 minus P2, okay, and this equation in this equation m can be determined by the values at operating point P. Okay. And the value of m, as I said, that we can get here is equal to C by this value. So, I can get that one here. Okay. And when I substitute this m value, I get the linearized equation. So, let us look at it. Suppose if I am given a C value like this, that is what actually I do is that for a given P1 minus P2 here, I find out what is Q, and from there I can get the value of C. So, if my C is say this value, that is 4 meter cube per second per under root kilopascal, and the corresponding this pressure drop value is say 8 kilopascal, and if I substitute this, I get value of m as this one, and I can substitute this value of m here, and this is what I get my linearized equation. Okay. So, this way I can get the linearized equation for our basic equation, which you remember it was Q is equal to C under root P1 minus P2. So, this was the nonlinear equation, and this nonlinear equation has been linearized into del Q is equal to 0.707 okay, del P1 minus P2. So, this is the linear version of it. Now, let us take another example, say a thermistor. Now, this thermistor, as we know, it is used to measure the temperature. Now, the relationship between the resistor R of the thermistor and the temperature T is given by this equation. Okay. You can see that there is a exponential variation. Here your K and C are the constant and T is the temperature. Now, I can linearize this equation about an operating point, say T0. So, what happens? Then the slope of the graph of R versus T at the operating point can be given by this one. That is, I just differentiate this previous equation. I differentiate this equation and I find out the dr by dt are the slope, and this is the slope. Then the linearized equation can be given by del R is equal to m del T, as we have seen previously, and I can substitute the value of m from here. Okay. And here you see, I know the constant K, I know the constant C, I know this T0 also because I know my operating point, and thus I get this equation delta R is equal to this constant into delta T, and this is what we call it as the linearized equation for this nonlinear equation. Okay. So, this was the small concept given to you to linearize the nonlinear equation. Okay. Now, why do we want to linearize a nonlinear equation? So, the reason for being is that there are ample amount of tools available for the linear systems, and once if you have linearized your nonlinear equation, you can always use those tools to study the various characteristic of your system, be it stability or be it say its frequency response or any other behavior. If you want to study about that system, there are many tools available. One such tool I have given, the Laplace transform, which all of you know that it is used to convert the differential equation into an algebraic equation, because we are more comfortable in dealing with the algebraic equation. Okay. So, with this I will close this talk. These are the two references which you can refer if you want to read it further. Thank you.